session. Our session chair is Wenpan. Can you hear us? I think our session chair is on Zoom. Wenpan, can you hear us?
Hello?
Oh, thank you very much. Can you please activate your microphone?
Yeah, can you hear me?
Yours.
Can you hear me?
Yes, we can hear you.
Great. Okay, good morning, everyone. Thank you for the introduction. I'm the chair for this session. So in this session, we're going to have some fantastic research paper about construction automation, construction robotic machinery, and state-of-the-art development in additive manufacturing, also as well as construction IoT. So our first presenter, our first paper is reinforcement learning with construction robotics, a review of research area, challenges, and opportunities. So the presenter is Xinghui Xu. So if you're ready, you can share your screen and the floor is yours.
Hi, everyone. Can you hear me?
Yeah.
Okay, yeah, perfect. Can I see the screens?
Yes.
Can I see the screens? Yeah, okay. Yeah, I will go on. Good morning, everyone. Thank you for giving us this opportunity to present our ongoing research. The topic of this research is reinforcement learning with construction robots, a preliminary review of research areas, challenges, and opportunities. My instructor is Professor Borja Garcia de Soto, and we are based in Abu Dhabi, the New York University, Abu Dhabi. Robotics have been widely used in many industries to assist human workers. When adopted into the construction industry, they can enhance productivity, efficiently reduce construction time, and increase safety in dangerous operations. With the expansion of the technologies, the construction industry has seen significant attempts on robotization in a semi-autonomous way, such as bricklaying, drilling, and ceiling installation, etc. These applications have shown promising results for single repetitive tasks to assist the human workers. However, some challenges still limited the higher level autonomous usage of such systems. For example, most of the applications work in a highly controlled environment. They are not smart enough to adapt the dynamic evolving of the construction site. Their motions and the workflow are pre-programmed by the expertise considering the characters and the orders of the task. Besides, these systems mostly semi-autonomous, which requires the interface of human workers to give orders. And furthermore, unlike workers collaborating on a construction project, most of these systems are developed with a single agent setting, which provide the potential to allow robots to collaborate in a group, just like how human workers works in the near future. So this research aims to train the construction robots to be more innovative. To overcome those limitations, a higher autonomous application should have the capabilities to react to the changes of the environment, obtain the motion and execution plan themselves, and then work together as a team to improve efficiency and accuracy. In order to make robots to be smarter, machine learning is an optimal way to train robots to find a solution. But in most scenarios, we need to specify a data set to tell the robot what we want. How about without giving these examples, can robots gain the skills themselves? As one of the solutions is like how human beings learn a skill. A sub-area of machine learning, which is called reinforcement learning, allows robots to learn from their own past experience. With practices and errors, they finally understand what is the best solution to achieve a goal. when it comes to complicated tasks such as construction work, the answers could be more complicated. Then a deep neural network will help to find a serial solutions in a massive options. Besides, a multi-agent reinforcement learning framework will allow them to learn in a group and understand how to collaborate with each other together. So this is the basic concept of the reinforcement learning. It is a circle that begins with observing a current state, choosing an action, and observing the received data. Actions lead to rewards, which could be positive or negative. Evaluation of how good this action will based on a reward that will lead us to an optimal policy. After that, the next circle begins. This is the scheme that how a training agent starts to understand the optimal strategy. In that paper, we did a SWOT analysis on integrating the reinforcement learning with construction robots. The training algorithms can help overcome the limitations mentioned above. Although there are still some other challenges, such as it is very hard to set up the simulator, or modeling the construction task, write out the equations, set up the constraints. But with the development of such algorithms and the potential of the mega data stored in the construction industry, there are still some promising outcomes in the near future. So in order to test the feasibility of combining these two technologies into the construction robotic applications, we present a simple case study that allows robots to pass finding in a dynamic working environment. We set up a waypoint for the robot to achieve by optimize the reward function to reduce the distance and angles between the robot and the desired location. After hundreds or even thousands of episodes training, when given a new initial point and desired point, the robot will find the shortest path to navigate to that location immediately, and also do the obstacle avoidance in a gazebo simulator at the same time. So the algorithm we are using currently in this simple test is DQN and DDPG. So based on that single agent setting, we further explore the possibility of multi-agent training, which allows them to collaborate. We allow multi-robots to work in the same working environment using decentralized and centralized training. In decentralized training, each agent learns its own policy, and the observations and the actions are independent. Other robots only act as obstacles when the robot is sensing the whole environment. The centralized learning approach assumes a joint global model for all the agents to act and to observe the environment. So it set up set all the robots into a closer connections. The figure shows the result of multi-agent reinforcement learning with these two methods. The decentralized training proved to be faster to converge than the centralized ones, because it has less computational burden to set up the neural network. So for the case study, here is the result. For the single agent reinforcement learning algorithm, we can solve the pathfinding problem with few iterations to train. And the computational resource grows exponentially from single agent to multi-agent. And in this case, the decentralized learning algorithm is better fit for these simple settings to do the pathfinding with less sample complexity and computational burdens. In conclusion, this paper discusses the challenges, opportunities, and research areas of the integration of the reinforcement learning with construction robotic applications. And we implement some very few algorithms in a simple case study to illustrate how they can be used in a construction robot application for path planning. So there's still some challenges and limitations at the same time. There are too few algorithms for test. There should be more benchmarking of different algorithms that is on the market to adapt to this kind of applications. And there are not enough construction tasks were simulated. Other tasks should also be adopted in the same training scheme to verify the results. And for the path planning, for the constraints and the rewards, we simplified those equations to make sure that it can converge in the end. The environment and the workflow are still controlled. More dynamic factors should be added, such as the relationship between different robots. We can set up the predecessors or successors, relations between each other, and teach them how to work together with different orders. So this is our future work. For future work, we will test more algorithms with a more construction-related framework. we will allow multi-robots bricklayer to build up a wall and assign different roles to them, such as bricklayer, material deliverer, and progress monitor. They will act in a sequential way, yet also in a dynamic evolving environment. We will teach them how to operate different tasks in a sequential order and to train them to generate and execution plan themselves. That's all from my side, and thank you for your attention. And if you are interested in our group, we are the Smart Construction Research Group located in NYU Abu Dhabi. Thank you for your attention. Any questions?
Thank you very much. Yeah, please, yeah, ask the audience. Yeah, do you have any questions from the audience? So I would like to ask a question if there's no question from the audience.
Okay.
What would be the, let's say, how would you describe the biggest, let's say, limitation right now for reinforced learning in the field of, let's say, construction robotics automation?
I think the biggest challenge currently is the simulator. Currently, we need to rely. Currently, we are building the simulator ourselves, but for example, this project we are using the gazebo to simulate the path planning for different robotics, but in real environment it could be more complicated. Currently, we assume that all the ground is flat and there are no other constraints. And the problem is just simplified, but with a more complicated simulation, with a more complicated situations, we need to modify the simulator. We need to maybe add, for example, we can just combine the beam information into the simulator. Currently, in the simulator, it is also static and it is not very evolving environment, which is not very compatible with the construction site. So I think the simulator is the most important thing for simulation. And after that, when we compile the simulation result to the real implementation, it is also another problem. There will be a lot of bugs. There will be a lot of deviations between the simulation environment to the real problem. Yeah, that's my thought.
Okay, thank you. Yeah. Maybe another question, just follow by your answer. Is it possible in the future for reinforcement learning to gather or learning, get data from based on the real time kind of a performance, like gather data from on site as the operation is kind of being carried out, and then decide somehow like use that as a base kind of a training model or data? I don't know.
I think that's a very good question. The training efficiency is also another challenge for this algorithm. That's why it is not very widely used, because it is like an experience to do something wrong. It will just learn from its failure, learn from its errors. So it will have a lot of iterations and exposed to do the wrong things after it figure out what is the right way to achieve a goal. So maybe if the situation is very simple, if the questions or if the task we are simulating is very simple, it will be quicker to converge to find the optimal policy or solution. But for more complicated tasks such as construction tasks, I think it may request millions episodes to run for a perfect run for right answers after we got that achieve that goals. So the efficiency is also a problem. So maybe in the future with the development of the algorithms, it will be faster, but I don't think it will be real time for this kind of that's why I think it's another limitation for this kind of algorithms. But at the end, it has a potential because we don't need to generate very huge data set. That is also very time consuming, and we can train the robot to think themselves. We don't need the robotic expertise to hard coding all the motions, all the trajectories. that's the goal for using this kind of algorithms.
Okay,
That's
thank you
my
very
answer.
much. Yeah,
Mhm.
for your answer, and thank you for the presentation. So yeah, great. Maybe we move on to the next presenter.